We're now going to begin our study of fields and field theory, and our first step in doing that is to understand vector spaces. Now, most of us are familiar with the ideas of vector spaces from linear algebra, and the ways that we're going to describe them and talk about them are really only a slight generalization of that. So let's start with the definition, 149. So let's let F be a field. A set V is an F vector space, or sometimes just vector space if the field F is determined. If V is an additive abelian group, and there is an operation which is a function taking an element of the field and an element of the vector space and giving back an element of the vector space, which is called the action of F on V. And then for any A in F and V in V, this means that AV, or sometimes A times V, sometimes we'll make the multiplication between them explicit, but we don't have to. This is an element of V, and then this action satisfies the following conditions. I should say this is for all A and B elements of F and all V and W elements of V. First, we have that the action distributes across addition in the vector space. We have that the action also distributes over addition in the field. We have a sort of associativity requirement where if I take B, if I look at the action of B on V, I get an element BV in the vector space V, and then if I apply A to that, I get another element of V, and this is the same thing as if I took A and B together and multiplied by V. And then finally, the unity element, the multiplicative identity, must act trivially on the vector space. It must send every V to V. Now you'll notice that these are exactly the properties that scalar multiplication has when we think about linear algebra and vector spaces there. This is completely correct, and what we're doing here in this definition is just a very tiny generalization of what you've likely seen before in linear algebra. What I do want to mention is that this same definition can or a modification of this definition also exists where we don't require that F is a field. If we just take a ring, replace F with R's throughout, and then we get the definition of an R module. Given time, we may be able to look at that later in the course. But just know that this is the specific case of a more general idea called modules. Now, vector spaces are much better behaved in general than arbitrary modules because we're working with fields, which are much more well behaved than arbitrary rings. All right, so let's see a few examples. Our most important example will be the vector space Fn, where this is the direct sum of n copies of F, and the elements of this vector space are ordered tuples, A2, A1, A2, AN, where the AI all belong to F. This is our very standard vector space that we're used to. If F here is the real numbers, then we'd be looking at n-dimensional real vectors here. Now, when I use this this plus notation here, this is the direct product of groups. The field F is a group under addition. Now, this is also a direct product of rings, and this set of elements has a ring structure using component-wise multiplication, but when we're talking about things in terms of vector spaces, we're not concerned with the multiplication there, we're only concerned with the addition in this vector space, and then multiplication by elements of F. Whenever we describe a vector space, we need to describe the action of F on that vector space. And so we need to say, if we take an element of F and we multiply that by some element of the vector space, we need to say what we get. And in this case, we're going to take this this scalar multiple b and multiply it by each one of the components inside the vector space. This is our most important example of a vector space. We will see that in many cases it's our only example of a vector space, but we're going to come back and circle around to that at the end of this section. Now, there are lots of other examples that we can have. We can look at the set of m by n matrices with elements in F. And so this is the set of all matrices of the form A11, A12, down to AMN, where all the aij's come from F. Now, the set of m by n matrices is a group under addition. Multiplication is not even defined on this if m and n are different sizes. And then again, we want to say what we get if we multiply one of our vector space elements by an element of the field. And again, in this case, we're going to get that just by taking that element and multiplying it by each one of the entries of the matrix. So that's another example of vector space over F. Now, in both of these cases, the vector spaces that we deal with can be described using finitely many, a finite amount of data. That is, in this first example, every element can be described using n elements of the field F. This second example every element can be described using m times n elements of F. But there are some vector spaces that don't have that can't be described using a bounded amount of data. The easiest example would be the set of polynomials over a field F. This is a vector space over F. Now, in this case, we have that F adjoint X is a ring, but in particular that means that it's an abelian group. And if I take any element of the ring and multiply it by any element of the polynomials, we get the polynomial where we multiply each one of the elements by the element b. Now, the reason why this is different than the other examples we've had so far is that there's no limit to how many different field elements you'll need to describe the various elements of the vector space F adjoin X. Given any polynomial can be described using finitely many coefficients here, a0, a1, up through an. But if we want to find a degree 1 million polynomial, that has to be described using 1,000,001 coefficients. And in fact, given any number, you can always find an element of F adjoin X that needs more than that many field elements to describe. So once we get there, it's going to turn out that our first two examples are examples of finite-dimensional vector spaces, and this down here, F adjoin X, is an infinite-dimensional vector space. But it's going to take us some work to be able to define dimension properly and make that statement explicit. All right, so we can generalize this example quite broadly and get to an important idea. Given a field F, a ring R, and any ring homomorphism, phi from F to R, I should say any non-zero ring homomorphism, phi from F to R, let's see, sorry, field F, we want, sorry, I do need to specify here that we need a ring, that the ring R has unity, and any non-zero ring homomorphism phi from F to R, we have that R is a vector space over F. Now, in order to prove that, we need to show how we can take any element of F and any element of the ring R and define an action of F on R that satisfies the conditions that we had before. So let's go ahead and do that. The way that we're going to define this is the following. We need to get an element of R out of this operation. Now, what we can do with A is we can apply phi to it, and we can get phi of A. Now, phi of A here is an element of the ring R, and this little r here is also an element of the ring R, and so we can multiply them together. So, the way that we have this written out, this is the action of F on R, and this is a product in R. So this is using the multiplication on R. Now, often we will be using a field F which sits inside a ring R, so that this ring homomorphism phi is just inclusion, so that phi of A is just basically A. And that's still valid, but it does apply more generally, and we're going to apply it more generally later. Let's just check, for the sake of practice, that this is a vector space action. Because the real key to being a vector space is the existence of this action which satisfies the conditions that you want. So the first thing is that we need to make sure that if we take A times V plus W, then we get A times V and A times W. Instead of V and W, I'll go ahead and use R and S to remind us that they belong to the ring R. So by definition, this is phi of A times R plus S. Because R is a ring, we have a distribution on the left, so this is phi of A times R plus phi of A times S. And since phi of A times R is the action of F on R, and phi of A times S is the action of A on S, we get what we want. Similarly, if we have A plus B times R, this is by definition phi of A plus B times R. Now, phi is assumed to be a ring homomorphism, which means in particular it respects addition. So we get phi of A plus phi of B times R. R is a ring, and so we have distribution on the right, so we get phi of A times R plus phi of B times R, which gives us A times R plus B times R. So we get the second condition that we need. For the third, we need to show that A times B times R is equal to AB times R. And this is going to go similarly to the one that we just did. So this is A dot phi of B times R. Now phi of B times R is now an element of the ring, and A is an element of the field, and so the action of F on R is given by phi of A times phi of B times R. The ring is associative, and so this is phi of A times phi of B times R. Phi is a ring homomorphism, and so this is phi of AB times R, which is the action of F on R with the element AB. And then finally, we have that 1 dot R is phi of 1 times R, and the image of identity is identity, and so we get R back. Apologies, I needed to specify further up here. We need that the ring R has unity, and also that phi of 1 equals 1. This is guaranteed if phi is surjective, but if phi is not surjective, then we need this extra hypothesis. However, this is not unusual. This is typically what we have in practice. All right, so given a field F and a ring R where we have a homomorphism which sends 1 to 1, then R itself is going to be a vector space over F. And we can build up a whole bunch of vector spaces over field F this way. Now, once we have vector spaces, we can also have subspaces. Definition 150 has that. If V is an F vector space, and then W is a subgroup of V, is also a vector space over F, then W is a subspace of V, or an F subspace if we need to specify the field. Note that if W is a subgroup of V, then the only thing we need to check to show that it's a subspace is that it's closed under the action of f. That is to say that A dot W lies in the subspace W for all field elements A and elements little w inside the subset W. So let's take an example. We've got the polynomial ring over the field F. This is a vector space over F. And let's let W be the set of all polynomials that are either 0 or of degree 3 or less. This is a sub-vector space of f adjoin x. Now, it's not a sub-ring of f adjoin x, because if we multiply, for instance, x cubed with x cubed, we get x to the 6th, which is not in W. So W is not closed under multiplication, but it is closed under addition and subtraction. It's a subgroup of the additive group f adjoin x, and it is a subvector space because if B is any element of the field F, and we take some element, any element of W, then the action of B on this element is also going to be a polynomial of degree 3 or less. And the point is that this is in W. Therefore, this set W is a subvector space of F. It's a subgroup additively. It's closed under addition and subtraction. And it is closed under the action of the field F. All right, let's look at another action, or another vector space. Let's consider the vector space R2. So this is two-dimensional real vector space consisting of all vectors of length 2. Now let's let V be the set R direct product Q, which is a subset of R squared. So we can we look at all the pairs where the first entry is anything at all, but the second entry is rational. This is certainly a subset of R squared. In fact, we can go further. It's an additive subgroup because the rationals are a group. And so the direct product of R and Q is a group. It's a subset of R2. Therefore, it's a subgroup of R2. However, V is not a subspace of R2. It's not a real subspace. So it's not an R subspace of R2, since it's not closed under multiplication by elements of the field R. And we can demonstrate this just by giving one example. So for instance, we could note that the element 0, 1 lies in V, but if I take square root of 2 times 0, 1, by definition, this is what we get when we take square root of 2 times each of the entries. So square root of 2 times 0 is 0, square root of 2 times 1 is the square root of 2, and the point is that's not in V. So V is not closed under the action of R, and therefore it is not a subspace of R2, even though it is an additive subgroup. All right, now a very important example we have is that we can construct a subspace out of a out of any subset of a vector space. So given a vector space, given an F vector space V, and W a subset of V. Now, any subset here could be finite, could be infinite, could be the whole thing, could be nothing. The only thing that we say is that we don't want it to be empty. The set W is said to be linearly dependent if there exist A1, A2, up through AN in F that are non-zero, and W1, W2, up through WN in W, such that A1, W1 plus A2, W2 plus dot 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 plus A1, W1 is equal to 0. Otherwise, the set W is said to be linearly independent. And I forgot to give this definition its proper notation here. So this is definition 151. So we can take a subset, and we can talk about whether the elements in it are linearly dependent or linearly independent. The idea here is that a set of elements in a vector space are linearly dependent if there's some non-trivial combination of them which is 0. Now, the trivial combination is where you just take 0 times each one of the elements of W, and you get 0 out of it. And they're linearly dependent if there's some other way of doing it. If there's some way of combining them together where you actually do include some of the vectors with non-zero coefficients, but you still get 0. If that's the case, then the set is said to be linearly dependent. Otherwise, it's said to be linearly independent. And the point of linear independence is that if you look at all of the vectors that you could possibly get as linear combinations of a linearly independent set, those representations will be unique, which is what's so important about it. Now, to make what I just said more precise, we do need another bit of terminology. So again, given a set W, which is a subset of V, the set consisting of all possible combinations, where the AIs just come from F, and the W1s and the WIs come from W. Notice that we're not assuming here that W is finite, so there could be infinitely many things in W, but we're only considering sums involving a finite number of them. This set is, well, first of all, it's a subspace of V. This is an exercise. And it's called the subspace spanned by W. Or sometimes it's the subspace generated by the set W. This is sometimes notated as F W. The idea behind this is that we're looking at all the ways of multiplying something by F by something by W, and then adding a bunch of those up. Or it's sometimes written using this notation, which is supposed to be reminiscent of the notation that we use for the generators of an ideal. By convention, the subspace generated by the empty set is just the the subspace consisting of the single element 0. Beg your pardon. All right, so we've got an idea of linear independence. We've got an idea of a subspace spanned by a set of vectors. Let's see some examples of these. The elements 3, 2, 1, 0, 1, 0, and 1, 1, 0 are linearly independent in the vector space R3. To see this, let's suppose that we have some element A times 3, 2, 1 plus element B times 0, 1, 0 plus some element C times 1, 1, 0, and that all gives us the 0 element in the vector space R cubed. Well, if we combine together all the things on the left, we get 3A plus C in the first entry. We get 2A plus B plus C in the second entry, and we get A in the third entry. And we want this tuple, this element on the left, to equal this element on the right. Well, we can see from comparing the third coordinates here that we must have that A equals 0. Well, if A equals 0, but 3A plus C equals 0, this means C would have to be equal to 0. And if A and C are equal to 0, but 2A plus B plus C equals 0, well, then B would have to equal 0 also. So what we found is that if there is any linear combination of these vectors that gives 0, then all of the coefficients of those vectors would have to be 0 also. So that means that the set containing the vectors 3, 2, 1, 0, 1, 0, and 1, 1, 0 are linearly, that's the set, is linearly independent. We can also see an example of a set which are not linearly independent. So we can take the elements 2, 3, negative 1, 0, 2, 5, and negative 6, negative 7, 8. Note that if we take 3 times 2, 3, negative 1, plus negative 1 times 0, 2, 5, plus 1 times negative 6, negative 7, 8, then we're going to get 0, 0, 0. And we can compare this component by component. In the first component, we get 3 times 2, plus negative 1 times 0, plus 1 times negative 6, which is 0. 3 times 3, minus 2, minus 7 is 0. Negative 3, minus 5, plus 8 is 0. So that means that there's a non-trivial linear combination of these vectors, which gives the 0 vector. And so that means that the elements 2, 3, negative 1, 0, 2, 5, and negative 6, negative 7, 8 are linearly dependent. Now, the point of being linearly dependent is that there are multiple ways of describing a vector in the span of your vectors as a linear combination of them. So in this case, we have that 3 times the first plus -1 times the second plus 1 times the third gives us 0. But if we took 0 times the first plus 0 times the second plus 0 times the third, we would also get 0. Or if we were to double all these coefficients, 6 times this plus -2 times this plus 2 times this would also give us 0. When you have a linearly dependent set of vectors, then things in their span can be represented lots of different ways. When you have a linearly independent set of vectors, vectors in their span have only a unique representation using those vectors. Now, a set containing a single non-zero vector is linearly independent, but kind of trivially. What we like about vector spaces is that we can find large sets of linearly independent vectors which have good relationships with the rest of the vector space. So we encode this in definition 152. Let's let V be an F vector space. A subset B of V is a basis for V, an F basis if you like, if B is linearly independent and V is spanned by B, meaning that every element of V can be expressed as a linear combination of the elements of B. Now, if B is a basis for V and the cardinality of B is finite, then the cardinality of B is called the dimension of V. All right. So the reason why we like bases is because given a basis B, every vector, or every element, equivalently, of V can be written uniquely as a linear combination of the B's. All right, so we have already seen that the set 3, 2, 1, comma 1 or 0, 1, 0, comma 1, 1, 0 is linearly independent in R3. Let's show that it's a basis for R3 by showing that everything in R3 is in the span of these vectors. In other words, by showing that every element of R3 can be written as a linear combination of these vectors. So, given some vector x, y, z in R3, we will find some A, B, and C in the field R such that A times 3, 2, 1 plus B times 0, 1, 0 plus C times 1, 1, 0 equals x, y, z. Now, if you write all this out and you write it out component by component, then you'll get a bunch of equations involving A, B, C, X, Y, and Z. If you treat the X, Y, and Z as parameters and solve for the A, B, and C, you'll find that after some work, you'll find that if we let A be equal to Z, C be equal to X minus 3Z, and b be negative x plus y plus z, that these work. If we let a, b, and c be these values, no matter what x, y, and z are, then when you plug them in, you get x, y, and z out of it. That shows that that this set of vectors spans all of R3, and therefore it's a basis. So this set of vectors 3, 2, 1, 0, 1, 0, and 1, 1, 0 is a basis for R3. Now, there's one big thing that we need to do, and that's to justify part of what we've done in definition 152. In definition 152, we said that if the vector space V contains a finite-sized basis, then that size of basis is called the dimension of V. What we have to show is that this is well defined. So what happens if we have two bases for V of different sizes? Let's suppose we had a basis of dimension 6 and a basis of dimension 7. Well, then is V a 6-dimensional or 7-dimensional vector space? More broadly, what if we had a basis B which had 10 elements and a basis C which had infinitely many elements? Then do we say that V is a finite-dimensional vector space or an infinite-dimensional vector space? Well, the good news is that none of these situations that I've just described can happen. If V has a finite basis, then every basis for V has the same cardinality as that one. So we can, in fact, refer to the size of a basis of a vector space V, but proving that takes a little bit of work, which is what we're going to do now. So, Theorem 153, which really is required in order to justify our terminology of the dimension. Let's let V be a vector space. Let me be precise here. Let's let V be an F vector space. Now, if B and C are bases for V, and if B is finite, if B is a finite set, then B and C have the same cardinality. So in other words, if V has any finite basis, then all bases of V have to be that same size. All right, so the proof here is going to require a few steps. So the first thing we're going to do is we're going to prove the following claim. If B, which goes from B1 to Bm, is any basis for V, and little v in V is any element such that this little v is equal to a1 b1 plus a2 b2 plus dot 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 plus am bm with the ai's belonging to f. We know that this is always going to be possible, and aj non-zero for some j, and that's always going to be true as long as v itself is non-zero. Then the set B prime, which is given by B1, B2, up through Bj minus 1, V, Bj, up through Bm, is a basis for V. So this claim is saying that if we've got a basis, then we can replace one of the basis elements with some other element of the vector space V. And in fact, we can replace them in a lot of ways. In fact, if you've got any basis of V and you choose any non-zero element of the vector space, then there's going to be some element of your basis that you can replace it with. So what you need to do is you take your element V, you express it as a linear combination of your basis vectors. That's always going to be possible because you're starting with a basis. You look at for any basis element Bj which has a non-zero coefficient in this expansion, and any one of them will do, and then you replace that jth basis element with V, and you've got yourself a new basis. So this is the claim. And once we have this claim, we're going to use this to sort of transform the two bases in the statement of the theorem. All right, so let's see that this claim works. So the proof of the claim. Let's suppose that we need to show that that this new set B prime is linearly independent and spans all of V. So we're going to show linear independence first. So let's suppose that we've got a sum of elements of B prime that equal 0. Now the elements of B prime look like Bi. I just noticed this. This is very important. In our notation for B prime, we're replacing the jth B element with V, which means that our new B prime goes from Bj minus 1 to V to Bj plus 1. So we haven't changed the size of the set, we've just replaced the jth one with V. Sorry about that. That notation was wrong the way I had it before. So the elements of B prime look like a whole bunch of Bi's for i's not equal to j, and V. So let's suppose that we've got a sum of a bunch of Ri, Bi, where these Ri's come from F, and let's suppose that we got a linear combination of elements of B prime which equal 0. So we have that 0 is equal to, as we had before, the sum of Ri Bi for I not equal to j plus Rj times V. Now, the point here is that we can replace V with something else. We have that V is equal to this sum here, and we get this sum for all I of AI times BI. And now if we rearrange it, this sum is over all i's, this sum is over the i's which aren't j's. So what we can do is say that, okay, for any I that's not j, we're going to have an Ri times Bi over here, and then over here we're going to have an Rj times Ai. So we get Ri plus Rj times Ai times Bi. And then the one thing that we have left is the term over here with I being equal to j, so we get Rj, Aj, Bj. So we turned our linear combination of the elements of B prime which equals 0, into a linear combination of elements of B, which equals 0. So now we've got a bunch of things times B's, all adding up to equal 0. Since B is linearly independent, we have that Ri plus Rjai is equal to 0 for I not equal to j, and we have that Rj times Aj equals 0. But remember what our hypothesis was. Our hypothesis is that Aj is not equal to 0. So since Aj is not equal to 0 and this product is happening in the field F, the field F is a domain, so that means that we must have that Rj equals 0. But if Rj equals 0, then all of these equations here lose their second term, so we get that Ri is equal to 0 for I not equal to j also. So all of the r's are equal to 0, which we used to describe our linear combination here. And so we can conclude that B prime is linearly independent. All right, so that's step 1. In fact, we could have broken up these two claims into parts in order to show that you could do this replacement and preserve linear independence. You could do this replacement and preserve that it spans the whole thing, but we're just doing them together. So now let's show that this set B prime actually spans all of V. What we know is that the set B spans all of V, and that's what we're going to use. All right, so now let's let W in V be any element. Now, since the set B spans V, there exist Ri in F such that W is equal to the sum over I. Let me back up over here. W is equal to the sum over I of the Ri BI's. But now we'll go ahead and do some computations with this to see that we can write W as a combination of the elements of B prime. So this is just splitting off the jth term. This is the sum of the Ri BI's with I not equal to j plus Rj Bj. But we can rewrite this further. We can say that this is the sum I not equal to j, Ri Bi plus Rj Aj inverse times Aj Bj. And the reason why we want to do this is because Aj times Bj is one of the terms in the expansion of V. And so Aj Bj is equal to V minus the sum of the Ai Bi's for I not equal to j. So V is equal to this whole sum, including all the i's. And so if we subtract off all the ones except j's, we would get the jth product here, Aj Bj. So expanding this out, we get Rj Aj inverse times V minus the sum I not equal to j of Rj Aj inverse Ai Bi. And now the two sums on the left and the right are summing over the same entries, and so we get that the sum from I not equal to j of Ri minus Rj Aj inverse Ai times Bi plus Rj Aj inverse V. And so, in particular, what this means is that this element W, which was arbitrary, can be expressed as a linear combination of the BI's, where I is not equal to j, and V. So this means that B prime spans all of V. Hence, combining these two things, that B prime is linearly independent and spans all of V, we have that B prime is a basis for V. All right, so this proves the claim. Now, once we have the claim, we're going to be able to apply it repeatedly in order to prove the statement of the theorem. So let's go to that. So now let's prove the statement of the theorem. Without loss of generality, we may assume that the cardinality of B is less than or equal to the cardinality of C. If the cardinality of C is infinite, this is guaranteed because the cardinality of B is assumed to be finite. If they're both finite, then we can simply switch the roles of B and C if necessary to make B have a cardinality no greater than that of C. So let's label the elements of B as B1, B2, up to Bm. And let's let C1, C2, up through Cm be distinct elements of C. We know that this is possible because C contains at least as many elements as B. And then, if possible, choose another distinct Cm plus 1. So basically what we're going to show is that the existence of an m plus first element in C is going to break things. So we're going to show that C, the cardinality of C can't even be 1 greater than the cardinality of B. But we're going to start by taking these elements C1 through Cm. Okay, now for k equals 0 to m, let's let B sub k be C1, C2, up through ck, comma, bk plus 1 up to bm, where it's implicit in this notation, but just to be explicit, b0 is defined to be b. So as k increases, we're replacing elements of our initial basis b with elements of C. And yes, as you're guessing, we're going to use the claim to show that each of these bk's is a basis for the vector space V. Now, it turns out that there's going to be some relabeling and some reordering going on here. So we're being a little fuzzy here. I'll try to point out where we're being a little fuzzy later on, but the principles are all correct here. All right. So we claim each bk is a basis for V, and we're going to prove this by induction on k. So this is clearly true for k equals 0, since b0 is equal to b, which is a basis by hypothesis. So now, let's suppose that bk minus 1 is a basis for V. Now, bk minus 1 involves C's up to the k. It has the first k minus 1 C's, and then it has the remainder of the elements in it being B's. Now, since bk minus 1 spans all of C, spans all of V because it's a basis, we have that the kth C term, ck, is equal to the sum of the elements of bk minus 1. And so I'm going to write that this way. It's going to be the sum of a bunch of ci's, where they've got some coefficients ri's, and it's going to be the sum of a bunch of bi's, where the bi's also have coefficients ri's, and the first sum is over i's less than k, so going up to k minus 1, and the second sum is from k onwards. Now, if Ri were equal to 0 for all I greater than or equal to k, then CK would be a linear combination of the set C1 through CK minus 1. So the set C is not linearly independent. A contradiction. So that means that Ri has to not be equal to 0 for some I greater than or equal to k. We can relabel, and this is the relabeling that I mentioned before. We can relabel so that Rk is not equal to 0. So in this sum right here, we've shown that one of the terms in this second sum must be non-zero. We'll relabel the b's in order to make it so that it's the kth one that has a non-zero coefficient in this sum. Basically, what we, to be completely precise about this, we would be proving that there exists some ordering of these B1s through BMs so that all of these BK sets are bases. However, putting all that together made the whole proof far more wordy and obscure. But that's the idea behind what's going on here. So we'll relabel so that Rk is not equal to 0. So we have that we have the set bk minus 1, and we've expressed an element of our vector space as a sum of those things. We have that sum has a non-zero coefficient in the kth position, so the coefficient of bk is non-zero in this description. So by the claim, we may replace the bk with the ck. So instead of the bk that was here before, we can put in the ck and then get bk minus 1 up through bm is a basis for V. And we can keep doing this over and over and over and over again, replacing more and more of the original B basis elements with the C basis elements. All right, now eventually we're going to get to the nth point. So this means that this Bm, which is what we get after we've replaced all of our B basis elements with C's, this is a basis for V. So now, if cardinality of C is strictly greater than the cardinality of B, then we would get that Cm plus 1 is a linear combination of elements in Bm. So that would mean that the set C1 through Cm plus 1 is not linearly independent. Which is a contradiction because we assumed that the set C, the whole set C, was linearly independent. So hence, so not linearly independent, a contradiction. So it can't be the case that the cardinality of C is greater than the cardinality of B. So it must be the case that the cardinality of C is equal to the cardinality of B, which finishes the proof. So this was a lot of work, but it winds up being extremely important to us. Knowing that all bases of a finite dimensional vector space are exactly the same cardinality is extremely helpful to us. So, in particular, this means that we can prove that a given set is the basis for, or is a basis of a vector space where we know the dimension in a couple of different ways. So let's let V be n-dimensional. Well, then a set and B a subset of V. So B is a basis for V. We want B to be a subset of size n. So B is a basis for V if and only if B is linearly independent which happens if and only if B spans V. So if you know the dimension of your vector space and you've got a subset which has the right size, then you just need to check one of the conditions of being a vector space and the other one comes through on its own. The basic idea here is that the more vectors you have, the harder it is for them to be linearly independent. One non-zero vector is always linearly independent. And as you go up, you've got more and more possibilities for some combination of those vectors to give you 0. On the other hand, as you have fewer and fewer vectors, it becomes harder for your set of vectors to span all of V. The set V spans V fairly trivially, and then you start cutting things down from that, and things get harder, and a single vector will not span your vector space unless you're one-dimensional. And so what happens, what this theorem shows, is that there's exactly one point where those two properties can exist simultaneously. The place which is the maximum size of a linearly independent set of vectors, that number, is the same as the minimum size of a set of spanning vectors. So, if you've got something that you know is n-dimensional, you've got a potential basis, if it's the right size, then you just need to check one of the two conditions, linear independence or spanning. And depending on your situation, one of those could be easier and one of those could be harder. Alright, let's take an example. Let's let F be a field. The vector space Fn is n-dimensional. To prove this, we need to give a basis for this vector space of size n. So this is true since a basis for Fn is the set 1, 0, 0, 0, 0, 0, 1, 0, 0, etc., 0, 0, dot, 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 1. So you look at the set of all the vectors that you get, which have zeros everywhere except in one of the components, and in that component you have 1. This is easily seen to be a basis for Fn. The fact that it's linearly independent is very easy to see, since each of these vectors, or each possible position, is only non-zero for one of the vectors. So if a linear combination of them is 0, then all the coefficients have to be 0. And it's also fairly easy to see that it spans all of Fn, because if you want to find a linear combination of these vectors that gives you a particular tuple, well, then the coefficients are just given by the entries of that tuple in each position. So this is often known as the standard basis. From an algebra point of view, these are only easy to work with. There's no mathematical reason really to prefer this basis over any other most of the time, but it is very easy to work with. And so we do that often. All right, now let's take an example that would be almost impossible to handle without the principles of the previous theorem. So let's look at the vector space r to the 30th is not r to the 30th, sorry, r30 is how we usually pronounce that, is 30-dimensional. So that just based on the previous example. And for I going from 1 to 30, let's let bi be given by the vector I squared, comma I minus 1 squared, comma dot 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 dot, and we'll take the squares down until we get to 4, to 1, to 0, and then zeros afterwards until you get to the end. So we've got some really weird vectors here that have coefficients which are they're not linear relationships; they're quadratic relationships, one to the next, and so they're a little odd to work with. But we claim that the set of BIs is a basis for R30. Now, proving that this thing is linearly independent and spanning of R30 would be a bit of a pain. However, we do know that the size of this set is 30, which means we only need to prove one of those statements. We only need to prove either that this set is linearly independent or that it spans all of R30. In this case, linear independence is easier. So, let's suppose that we have a sum of Ri Bi's equaling the 0 vector 0, 0, blah, 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 0. Now, you'll notice in this construction that B30 is the only vector with a non-zero entry in position 30. So this means that R30, its coefficient here, must be equal to 0. Because if it were something else, then you couldn't possibly get a 0 out of the in the 30th position in this linear combination. So we can conclude that. Now, B29 and B30 are the only vectors with non-zero entries in position 29, so we must have that R29. So we must have that the coefficients of or the linear combination of the 29th entries between B29 and B30 go to 0. However, we already know that R30 is equal to 0, so we must also have that R29 is equal to 0, because if it were not, then the non-zero entry of B29 in the 29th position would give us 0, or would give us something non-zero otherwise. We can continue this process to show that, to go backwards basically, and show that every one of these R values must be 0. That means that this set of vectors is linearly independent, and since it's the right size to be a basis of R30 and linearly independent, it is a basis for R30. And we were able to do that without referring to anything about spanning R30 at all. All right, last bit I want to do here is to talk about vector space homomorphisms, functions between vector spaces. So we'll give the definition here. It'll look very similar to other definitions that we've had, although it's going to be different in that it takes the action of f on v into account. So let's let v and w be f vector spaces. And f vector space homomorphism is a function phi going from v to w such that for all elements of f, for all a and f, and u and v in v, we have that phi of u plus v is equal to phi of u plus phi of v. In other words, phi has to be a group homomorphism going from v to w. And it also has to respect the action. So if I take phi of a times v, where a is an element of f, that's the same as a times phi of v. So it shouldn't matter whether we apply the action of f before or after applying the function phi. And a function phi which does this is called an f vector space homomorphism. Now, if this phi is bijective, we say it is an f vector space isomorphism. And we write, in this case, that v is isomorphic to w. Now, I do want to point out briefly that this symbol, this isomorphism symbol that we have here, is a little ambiguous. We've used it for a lot of things. We've used it to mean isomorphic as groups. We've used it to mean isomorphic as rings. We're now using it to mean isomorphic as vector spaces. And the sets v and w could be simultaneously groups and rings and vector spaces, depending on which way you look at it. And so when we write this isomorphism here, it could mean one of those three things. It's incumbent upon us, when we write down a proof, to make it clear whether we're using this symbol to mean an isomorphism in one way or another. Because it's very often the case that two things will be isomorphic under some structures, but not isomorphic under other structures. All right, so let's see an example, a fairly abstract example. If V and W are finite dimensional, vector spaces over a field F, a vector space homomorphism phi from V to W can be represented using a matrix. Now, we're used to doing this when V and W are vector spaces over, say, the real numbers or maybe even the complex numbers. The point is that we can do this with vector spaces over any field at all, and we're going to get a matrix with entries in that field. So to see this construction, we can let B1 through Bn be a basis for V, and C1 through Cm a basis for W. Let me pause here to say that while we haven't proven right now that every vector space has a basis, that turns out to be a true statement. It requires some set theory in order to prove it that we haven't developed, but every vector space has some basis or other. So we can do this. Now, for every j, from 1 to n, the element phi of bj, this is an element of W, and it can be written in the form a 1jc1 plus a 2jc2 plus blah 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 plus a mjcm. And we take any basis element in V, you send it over to W, it's represented as some linear combination of the basis elements of W. So now we can let A be the matrix Aij, defined this way. This is the M by N matrix with entries in F, in the field F. Now, for any element U in V, we may write U as a linear combination of the B's. So it's going to be U1 B1 plus U2 B2 plus dot 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 plus UN BN. Then it turns out that if you work through what happens, use the fact that phi is an F vector space homomorphism, the coefficients of phi of U in W are given by the column vector A times the vector U, where U is the column vector U1, U2, down to UN. So A is an M by N matrix, U is an N by 1 column matrix. The result of that will be a column vector with entries in F, and it's going to give the coefficients of the C's, of the C basis in W, of the entry, or of the element phi of U. So these sorts of ideas that we developed for real vector spaces or complex vector spaces work in pretty much exactly the same way when we're working with vector spaces over an arbitrary ring. Now, the most important consequence to this idea about vector space homomorphisms is the following result, the proof of which is left as an exercise, Theorem 155. Let's let F be a field and N some non-negative number. If V is an n-dimensional vector space, then V is isomorphic to Fn as F vector spaces. As I say, the proof is an exercise. But what this theorem says basically is that there's only one vector space of each dimension up to isomorphism. What this means from an algebra point of view is that if we just study these Fn vector spaces, that incorporates all possible structures of any finite dimensional vector space, which is very nice because these Fn vector spaces have a very nice structure. They've got their standard basis that's very simple to work with, and Theorem 155 shows that every n-dimensional vector space essentially behaves like the Fn vector space that we had before.